Hello everyone, welcome to another video where today it's actually the first video that I'm recording in the United Kingdom. So I guess I should not say hello everyone, but something like Tallyho. I don't know how this works here, I'm still new here. Either way, I found a new flat earther that we haven't talked about yet. His name is Todd Peachy, and apparently basics physics proves the Earth is not in motion, which would be certainly interesting for someone who's currently doing his master's degree in physics like me, and one in astronomy as well. So let's see what I missed in my studies so far, apparently.
Hey everyone.
Hello, Todd.
You globies are going to want to stick around because I'm going to give you something to think about. If we were orbiting and spinning like they say we are, it would be self-evident. And when I say...
I mean, it frankly, if you were to open your eyes, I do believe that it is self-evident, but please do explain why you think it's not.
Self-evident, I mean self-evident. You would know if you were orbiting at 66,000 miles per hour and spinning at 1,000 miles per hour.
I mean, do you mean know in the sense of we would know instinctively? Or do you know in the sense of it would be easy to test, because it is comparatively easy to test?
Equator, of course. It's a standard practice of both sides of this argument to just use the equator at 1,000 miles per hour as a standard.
That is correct, and for a change, I will replay him at normal speed because he actually talks rather quickly. Yes, it is a standard practice to use the tangential velocity at the equator, and that's perfectly fine.
So, at the equator, any object on the Earth would experience a 2,000 mile per hour fluctuation twice a day. This is because...
So, first of all, I wouldn't call it a fluctuation, it's more like an oscillation. Fluctuation usually has an element of randomness in it. That is certainly not the case with that thing, but yeah, we do. There is actually a change of acceleration measurable when you move from the poles towards the equator. That's also why very, very sensitive scales, like for measuring gold and other fine minerals like that, actually have to be calibrated before use, amongst other things, because of that. There is actually a video from, I believe Bob the Science Guy, could be wrong, where he shows when he went to on holiday, where he showed that near the equator his 100 grams that he set his scale to actually weighs less at the equator due to this effect.
Because as you're spinning 1,000 miles per hour, when you are in the same line with the direction of the orbital path, you would be adding 1,000 miles per hour. Then when you were on the inside of the orbit, you're going back against the direction of the orbital path, so you would have to subtract 1,000 miles per hour.
I mean, it would be the same regardless if we're orbiting or not, right? I mean, if that's just how rotation works. If you have something that's rotating on the one side, it will be moving with a velocity vector that goes to the exact opposite direction, and it is on the other end of what you're rotating. That's kind of how rotation works, right?
Now, this is not argued by globies. This is simple physics. It's the way it is. Just the same way that a bicycle wheel doesn't spin as fast towards the center as it does towards the outside.
Well, the tangential velocity is less there. They spin equally fast. Rotation is given in some amount of angle per time, like radians per second would be the SI thing, way to do things. You could use rotations per minute if you want. You can use any arbitrary angle as long as you define it per any arbitrary time as long as you define it.
If it didn't have those variations in speed, you wouldn't have a spinning wheel.
That's correct.
So we're talking about something that can't be argued unless, of course, you want to rewrite physics. So we're going to start there.
I'd certainly like to, but I think my chances there are very slim.
Let's add a visual picture to it. When you're spinning along with you,
I love how the visual picture is in the top third of the already tiny image. That's just, I mean, I understand if you do it with your phone, it's kind of difficult, but I find that that's funny.
Earth, here's the orbital path, 66,000 miles per hour.
Why are you going on the orbital path? The orbital path plays no role here. This would be the same if Earth wasn't rotating. I don't understand. This has nothing to do with the orbital path, but sure.
When you're on the outside going in the same direction, you add 1,000 miles per hour. When you're on the inside, you're going back against the direction of the orbital path, so you subtract 1,000 miles per hour.
I think we all understand that, yes.
I'll let P-Brain reiterate.
Hours would have a...
I don't think it is necessary. We understand. Yeah, sure. We get it's addition. We have that figured out, my dear.
Hours every day of the year.
Now we're going to listen to one of the most smart-mouthed, arrogant, and cocky globetards on the market explain why we wouldn't feel this motion. And then I'll explain to you...
Again, it's not fluctuating, it's more like oscillating, but the acceleration actually is constant because you are on a spinning surface. The rotation, if you will, this kind of rotation will manifest as a centrifugal force that is tiny. It's about it's a bit over, just above 2. What's the unit there? Centimeters per second squared, I think. So like in the order of like 1 or 2% of 1 or 2 per mil of what the actual gravitational attraction is.
He went wrong, and how we would.
Okay, you know what? Let's humor him. I'm going to use his numbers.
More accurately, he's going to use the correct numbers according to physics.
Again, in the top third, love it.
So we're talking about everybody's numbers.
He says it's 2,000 miles per hour every 12 hours. Okay,
that's correct.
So that's 166 2/3 miles per hour every hour. Okay,
Sure.
That's 2 7/9 miles per hour every minute, or 0 to 60 in 21.6 minutes.
My point exactly. The acceleration that you would feel if the human body could detect such a small acceleration reliably would be absolutely tiny, and in fact it's kind of the acceleration that you feel is not how should I say it, because you're rotating, right? The constriction of your available movement path will force a curve, and that's why you feel this acceleration outwards, away from the motion. When you take a ball and you tie it to a string, and then you can whirl this construction around, right? The force that the thing feels in the ball feels will be outwards. That's why the chord the chord becomes like it straightens out, right? When you spin it around. Yeah. No, that was quite correct there. I'm afraid he's quite right. Yeah. Oh, yeah.
That's where you go off track, kid. I'm gonna let him ramble for a little bit, just so you can see for yourself how stupid he is.
Okay.
I'm quite afraid it is not he who is stupid here.
For comparison's sake, an object in freefall on planet Earth.
No, that's a bad comparison. I wouldn't compare it to freefall. First of all, because the two forces that we're talking about go in opposite directions, so it's kind of not ideal to compare them, because you're always going to feel both at the same time. So like that's not intuitive. If one is kind of a part of, like if both are part of the net force that you feel, it's kind of not intuitive. And also, I refrain from using gravity in a comparison when it is to actual mechanical acceleration, just because objects in free fall, strictly speaking, fall on a geodesic, and that's a kind of where the force is zero in general relativity, and not it's of course we don't need GR in this context, but it's a bit more complicated than that.
This is going to experience an acceleration of 9.8 meters per second per second.
That's true.
And that you can definitely feel. You could definitely feel it if you were falling, right?
Yep.
The acceleration...
I mean, you can't, because when you're falling, you're force-free, really. But so, kind of a bad example here, my friend.
This guy is worried about, though, is 0.02 meters per second.
Yeah, so that's correct. So around 2 point something centimeters per second squared, yes.
Per second. So try to imagine, if you will, falling, but at 0.2% the normal rate that you'd fall on planet Earth.
I mean, strictly speaking, you're correct, but I prefer the car acceleration example from earlier. This shows better, I think, how weak the centrifugal force from rotation really would be.
You can't. I bet you can't do it. You know why? Because
Yes, we do know why.
Yeah, because gravity is a constant, kind of another poor example, I think, but okay.
It's because you are asking us to imagine something that is not familiar to us, or you, or
you
anybody.
wouldn't even feel it.
What the kid's doing is breaking the 2,000 miles per hour over 12 hours down into average rate of change.
Yeah, because that's how acceleration works. You have a velocity over a set amount of time, so you take the velocity, you divide it by that time, and in SI units you would get something in meters per second, or as we say, meters per second squared.
2,000 miles per hour over 12 hours is 166.66 miles per hour.
It is not. You just said that 2,000 miles per hour over 12 hours. So your results cannot be in miles per hour. You have dropped 1 per hour. If anything, it's 166.7, let's say, miles per hour. You just made a velocity out of an acceleration, which kind of shows me that you really don't know how units work. That's a really poor thing to do. When I do the introduction, I did 3 times. I think I was a exercise group leader, kind of. I think is the literal translation for starting students at the physics department. And one of the first things that we teach them is look at your units. If the units don't make sense, this will leave a really, really bad mark, because everyone thinks you didn't look through your units, and B, your results are likely very wrong.
Per hour. That breaks down into 2.77 miles per hour per minute.
Per minute squared, please. Still, you have an acceleration. You can't make a velocity out of an acceleration.
Then he goes off the rails, puts it into unrelatable terms, 0 to 60 in 21.6 minutes.
How is that unrelatable? That is what those numbers mean. It's not his fault that the force felt from rotation is so small.
Can you relate to that? Have you ever been in a vehicle or a boat or anything and went from 0 to 60 and made sure you took 21.6 minutes to do it? I haven't.
You could go ahead and do that to see if you would feel the acceleration, you know. But
I don't doubt if any of you have either. What you should have done here is to break it into terms that you can relate to, something that you work with on a daily basis, something that everybody understands.
Physics is under no obligation to be broken down or make sense to you or anyone for that matter.
2.77 miles per hour per minute breaks down into 0.046 miles per hour per second.
Suddenly we have the acceleration back. That's nice.
Now that...
Yeah, that's still the same though. Imagine with that velocity, it would take you ages to even reach 1 miles per hour.
Is unrelatable.
That's correct.
0.046 miles per hour per second.
You know, it's also unrelatable Boltzmann's constant, and yet it's still the right thing to use in a lot of contexts. So, like, just because it's unrelatable doesn't mean that it's not true, you know, right?
He goes metric.
Also, it's a nice way to not address things by saying, "Oh, it's not relatable." Well, yeah, duh.
Where he likes to jump back from standard to metric, which is not a good practice.
Standard to metric. It's only standard to what, like less than 10% of the world's population. So really, you are using imperial when you should be using "quote unquote" standard. I mean, there are literally called standard units, the SI units. You know, so. If anything, it's your problem.
Practice, if you're not trying to confuse people.
Only people are confused by that who can't fathom 2 different units of measurement.
So, how do you put that into relatable terms? Well, with speed, miles per hour.
No, miles per hour per second. Or, I mean that's still a pretty stupid unit. Why not use miles per second, or like meters per second squared? You know?
You have a distance, correct?
No! You can't make a distance out of an acceleration either. My dude, what's going on? I mean, unless you cut in a fixed amount of time when you say that you only have an acceleration and you have this acceleration acting on the body for 5 seconds. Of course, you can calculate how far the object has traveled, but I don't think that's where you're going.
0.046 miles per hour per second breaks down to 0.81 inches per second.
It does not. We're back at a velocity again. You flip-flop with the thing. Okay, it was an acceleration. You had length per time. And now you have length per time. Do you see how you can't just do that? It's like me measuring distance in amperes. That doesn't work. I can't say my phone is 8 amps away from me.
This means that every second of the day,
sorry,
you would be going 0.81 inches further.
No, it would not. Okay. Again, he seems to have severe difficulties understanding the concept of acceleration, which is really just a change of velocity. But let's hear him out, right?
Than you did the second before. So your feet are on the earth. They would go that extra distance because your feet are touching the earth, and
your body is touching your feet, so they would go with it. You know that when Earth rotates, and it has rotated since you were born, right? So you are moving with the Earth constantly. You are aware of that, right? That's like the good old helicopter argument when you say, oh, if a helicopter takes off, why can't it just wait 12 hours and be at the other side of the Earth? Because the helicopter has the same momentum as the piece of ground that it just took off from, right? It's the same with your feet. According to your logic, if you were on a train and the train was going at, say, 10 meters per second, right? Then your feet would move 10 meters every second. You would have to fall over in like less than half a second. But that doesn't happen. I wonder why. How? Todd, please explain to me. According to this logic, how am I able to walk in an airplane? I flew here to the UK a couple of weeks ago, right? And when I fly back, I can take a wee on the plane, and somehow I can just walk in the plane. Is that maybe because during the start, during the takeoff, I got the same momentum or the same velocity as the plane, and when I make a step, my momentum is conserved? This, I really shouldn't be explaining this to you. You're a grown-up, you should know that. I just do hope you have like object permanence or things like that.
Your upper body would try to stay where it was. So you're going to be...
Well, if it was accelerated motion at 0.8 inches per second, or per second squared, and you were previously not moving with whatever is accelerating, then yes, that would indeed be an issue, right? We are not, but the acceleration, not only is it very, very little, as we have shown with like super duper small, it's also acting outwards from the center of the Earth, because that's how centripetal forces work when you're rotating. And it's also, you are moving with the surface of the Earth. You have the same velocity. Actually, your head even has slightly more, because it, strictly speaking, is further away from the center of the Earth, right? And the angular velocity is the same, and the velocity is just angular velocity times the radius. So your tangential velocity of your head is higher than that of your feet, but only like for 1 millimeter per second in absolute terms. So that's like nothing, or even no less than that, at 0.1 millimeters per second, if I'm not mistaken here.
3/4 of an inch off every second, and in about 5 seconds you're going to be rocked up on your heels and like, whoa, and you're going to have to lean to compensate for that.
Todd, please tell me, have you ever been on a train? Does that happen when you're on a train? I don't think it does.
3/4 of an inch every second is well enough to measure, observe, and be self-evident. Or you'll be on your butt when you get to the 12 hours point where you go back or the other direction. Now you're going to have to lean the opposite way, because you're going to travel.
Oh dear. Okay. He thinks it's 12 hours one direction, 12 hours the other direction, when really you moving with the Earth, so it's like all the time a constant acceleration, right? And you need to think of this as a directional arrow, right? If you look at it from above, you have a directional arrow that goes straight up, and it takes it an hour to change by as little as 15 degrees. So this change of direction of this velocity arrow will be so small, you essentially don't notice it. And the thing that you notice will be outwards, because that's how centrifugal force works.
0.81 inches less distance than you did the second before every second. Every second, 3/4 less, 3/4 less. Now, if a globie or if anybody that understands physics wants to try to argue that you would not feel and be very aware of 0.81 inches change every second, well, then they need to go back to base.
0.81 inches per second is a velocity, my dude. When you're on the train, and the train, I have been in a TGV from, like, I think it was Milan in Italy to Paris this summer. Last summer. Some summer. And we were going 300 kilometers per hour in this thing. That's just a bit less than 90 meters per second. I was able to walk in that train, even though, believe it or not, that's a 90-meter change every second. Oh, crazy how that works. That's because my velocity is conserved. How can this man... No, I won't say it. I will remain friendly.
Or just bag the whole operation because they absolutely don't have a clue.
I certainly know someone who doesn't have a clue in this interaction here, yeah.
If you want to prove it...
little hint, it's not me. And I imagine that for Todd it's still not clear who I'm talking about.
So, get yourself a trolley car or something and have it accelerate that extra every second.
Yeah, you do that actually. You know what? Why don't you do that? Have a trolley car accelerate with about 0.02 meters per second squared. So like 2 centimeters per second every second. Like, right? Can you do that? Please do it. Please do it. To understand what we're doing. Please talk. I beg you do that.
And see for yourself. You're going to have to lean. The body is very sensitive. It's a very sensitive mechanism, and it's going to have to compensate for that so that you don't land on your tush or your roly-poly head. So,
I love how he had to clarify here that there are other options available than landing on your bottom.
Kid, you're wrong.
Even though his example was somewhat poor in my opinion, he was very correct.
Now, the real diehard globe tards are going to try to confuse you. And we're talking about hard...
I am sure that they confuse you.
It's like Greater Sapien, Simon Dan, Professor Dave.
Professor Dave. Great dude. Like him.
Baldy Cats. Who else? I mean, you guys know who we're talking about. They're all going to break it down into some negligible sounding motion.
It's not negligible sounding, it is negligible. Run the numbers yourself. Roughly a bit more than 2 centimeters per second per second. That's next to nothing.
When we're speaking of the motion of the Earth, you just can't say 1,000 miles per hour to Fight the Flat Earth Craig, because he just won't accept that.
Yeah, because even though I have my issues with Craig and how he handles things, he's very strict with that one. 1,000 meters per second or 1,000 miles per hour, actually in meters per second, that's like 450 something meters per second, is just not the unit with which to describe rotation. Rotation is described with radians per second, or rotations per hour, or per minute, or 15 degrees per hour, for example. That's also fine.
He immediately says, no, you can't measure it that way. You can't measure miles per hour. You have to measure it in degrees per hour. 15
Yeah, that's correct.
degrees per hour. Okay. Or he says 1 rotation per day. You know, that's slow, and he'll compare it to the hour hand on a clock.
those are all reasonable things to do. It is extremely so. Go get on a desk chair and rotate once every 24 hours.
It's twice as slow as the hour hand on the clock. Well, he's hoping that you will overlook the fact that we're talking about equivalent terms here. These things all equal each other.
They do not. If you want to have the tangential velocity, you need to multiply with the radius. So they're not equivalent. You need an additional piece of information then.
1,000 miles per hour is 1,000 miles per hour. Now, if you had the hour hand on the clock was as long as the radius of the Earth, guess what? It's going to be moving 2,000 miles per hour at the end. 2,000 miles per hour. So they're trying to say...
Well, I mean 1,000, but yeah, I get what you're saying. But that's not relevant. Because it's... My dude, please understand. You cannot feel linear velocity. Why don't you feel it how fast you're going on an airplane or on a train or something else that goes rather fast?
You wouldn't feel the Earth rotating in one rotation per day. That's twice as slow as the hands on a clock. Yeah, a 12-inch clock.
No, the force... My dude, calculate the force yourself. I don't think you can do that in any capacity whatsoever. And then tell me, and then take... That's actually an example. And then take some weight in your, and put it in your pockets that corresponds to this force. It's the wrong direction then, but who cares, right? And then tell me if you feel a manageable difference. And actually, now that we're talking about it, the human threshold for feeling acceleration is just about where the difference is from the pole region to the equator. You would feel that difference if the change were like instantaneously, or like that's where the detection threshold is. So that's like the lowest limit that humans can feel. The issue, however, is that the way that our organs feel it, they kind of get used to this. So whilst you're flying from one spot to another, you kind of that kind of fixes itself, so you don't feel it in the end. Also, there are other factors that are important there, like local geographic gravity, because it actually depends on where you are on the Earth, not only how close you are to the equator, but also which kind of sediment is below you, which clothes you're wearing, and that there are so many other factors that are greater than that, and that's why we don't feel the acceleration, even if you would fly from very close to the poles to essentially the equator.
You guys are morons. Ugh.
I will leave this uncommented.
So, there you go. Basic physics.
Yeah, there you go, Todd. Basic physics. You have absolutely failed. I know middle schoolers who have a better understanding of physics than you do.
Physics, if you want to try to convince yourself that you would not feel a 3/4 of an inch change every second, if you want to think...
Yeah, again, that's a velocity. I don't know how else to explain it. That's velocity, that's speed. That's in old physics tiny books it's called tempo, if it doesn't have a direction, but yeah.
That wouldn't put you on your butt if you didn't compensate for it within 5 seconds. If you want to just step outside of known physics and start making up your own shit,
then your name is Todd Peachy. I think that's a nice conclusion to this video. Let's give him the last 30 seconds.
Well, all I can say is more power to you. Go ahead and just be as retarded as you want to be. You live on a flat, motionless Earth the way God made it. If we were doing all the crazy motions and spinning and twirling and orbiting like they say, it would be self-evident.
It is self-evident by quite a few examples, some of which I have listed on my channel.
Catch me in my next video, because I'm really going to put the screws to you. Another even more obvious falsehood of the globe will be torn apart.
Even more. I will leave you with that. I will now go and, I don't know, do something productive. Pick my nose or something compared to this. So either way. Thank you so much for watching in this somewhat limited setup with my laptop. I hope the audio was fine on this one. I had some audio troubles earlier. I hope it's fine now. In any case, I will see you in the next video. If you enjoyed this one, maybe consider leaving a like. If you enjoyed it a lot, considering subscribing. I'm Olaf from Olaf das Astro, and I will see you in the next video. Until then, have a good time. Goodbye!